eso mismo le dije yo. Eso le dije.
Empezamos con
Okay, well, so just a short peek. I mean, we have also Andres Chacoma that is studying here as a postdoc, so he's a new member of IFISC. So you will find him around in this corridor.
Okay, before we start the seminar, just to remind you, we have tomorrow a seminar at 1 p.m. and then we have lunch at 2. But the seminar at 1 is not here. The seminar is by here.
They have lunch if they attend the seminar, no?
There will be a checklist.
Well, okay. Good afternoon, everybody. It's a pleasure for me to introduce you Mariano Sigman. He's Argentinian also, like me. He studied physics. Eh?
You're Mallorquín.
Yeah, I'm also Mallorquín, but I was Argentinian. He studied physics in the University of Buenos Aires, and then he did a PhD degree in neuroscience in the Rockefeller University in New York. He was a postdoctoral researcher in cognitive science at the College de France in Paris. He has been awarded with very prestigious international academic prizes in his discipline, including a prize for the Young Researcher awarded in the College de France in Paris in 2006, the Career Development Award granted by the Human Frontier Science Program in 2017 and in 2007, and others. He's author of more than 100 publications with more than 8,000 citations. But he not only worked on neuroscience, he has a broad scope beyond the academy. His research had practical implications in medicine, in education, and also in art. He worked with magicians, chess players, musicians, plastic artists in topics of neuroscience related. In recent years, he has consolidated the bridge between neuroscience and education. He published books like La Pizarra de Babel or La Vida Secreta de la Mente. And he also developed extensive career in disseminating science with newspapers, in radio, television, and more. So thank you very much, Mariano, for being here.
Thank you, Claudio. Thank you. It's a pleasure to be here. I work in a variety of topics. One of something that I've been working continuously over the last years is decision making, and within decision making, how we construct confidence. Confidence is a broad sense of trust, and it applies to many different dimensions. So there's self-confidence, how much we trust ourselves being capable of doing things. There's confidence in other people, so whether we think the other people will betray us or not. There's confidence in the future. We can be optimistic and think that the future is going to be a good future. We can be pessimist. Confidence applies to many different dimensions, and we work on a relatively narrow window of confidence, which is the confidence that we assign to the decisions we make. So when we decide to go somewhere for vacation, we can be completely sure, and we are sure that this is the right choice. Or we are going there, but we feel that maybe there was a better choice, and we should have chosen something differently. In the restaurant, in every choice we make, we also have a feeling of confidence. So I would like first to give you a feeling, although, I mean, speaking of confidence is easy because we all know what it is, but still I want to give you two examples for this. One is a very general one, and it's confidence, it's social confidence. This is taken from Alex Todorov in Princeton, and there are many ways of playing this experiment. I mean, Alex works on trying to understand what aspects of facial forms make us judge people as being competent, trustable, serious, funny, etc., etc. And I'd like to play an experiment with you, so you get an idea of the kind of things that we do, which is psychological experiments. So this is how, many ways of doing this, but this is the way I like it, is like this. Imagine you have a suitcase, and in this suitcase you have like the most important things of your life. Actually, the experiment is what you would put in the suitcase, but this is going to be private only for you. You have the letters of your children, the pictures of your grandfather and grandmother, you have money, you have jewels, you have things that you don't want anyone to see. And those things are in a suitcase. They're very important. This is what I want to convey. And for some reason, you need to exit, you need to go somewhere and leave your suitcase. You can imagine a very basic things, like you have to go to the bathroom, for instance, and the suitcase doesn't fit through the door. And there you are with your suitcase that has the most important things of your life. And you go like this, and you look at these three guys, and you're gonna give it to one of them, and say, could you please hold it for 5 minutes? I'll be back. Please take care. It's the most important things in my life. I'll be back in 5 minutes. And so the question for you, decision makers and thinkers of confidence, is whether you give it to this guy, or to this guy. And you'll see, we run many of these experiments, but you'll see that there's going to be some variety here, but also within this variety there's going to be some regularity. This is the essence of what I want to tell you today. So the question is, who would give the suitcase to this guy here? Raise your hand. Okay, three. Usually it's males, usually big ones. I mean, it happens. Who would give it to this one here? To this one here? No one? Okay, usually there's 2 or 3. And to this one here? Everybody. Okay, good. You're humans. So humans are, I mean, you're all humans. Okay, so we, I mean,
I think it's the same guy, right?
yeah, it's the same guy, of course. It's only changed on the, it's only changed the curvature of the mouth and the curvature. But it's incredible how this actually makes very strong judgments on how we think about the attitudes of the other people. And so, some gave it to this one, no one, this is strange. Usually there's a minority here as well, and usually there's a majority here. What we all agree, yes. So what we all agree, and this is where I have to speak in Argentinian, is that this guy is a boludo. So there's a, no one would think that he's going to steal your suitcase, but he's so dumb and so distracted and so inattentive that someone is going to steal it from him. And you do not, it's like an Argentinian bank. This is like a Swiss bank. So, this is an investment judgment problem, right? You're choosing who to give your money to. And this is a bank, no one will enter this bank, but it may happen that when you come back after 5 minutes, they say, you know what, I like your suitcase, come pick it. And then you have an issue. And this is, of course, so the point with this, it's fun and it's an experiment, there's the point on this, which is how we build, even for very sophisticated assignments of confidence, these heuristics, which we're not even aware of. We didn't, at least if no one would have told me, I didn't know that I would choose and I would commit to a sense of confidence to the other people by the curvature of the mouth and the curvature of the eyebrows in a very mechanical way. So we have a very stereotyped way of assigning confidence, and this actually ends up deciding who we are, who we trust, who we give credit to, who we decide to be with, and so on. Okay, so now a much more boring experiment than this one, but this is the kind of experiments that we need for what I want to show you. Now those are letters, and letters are more boring than faces, but you need to look at them. And there they are, and now they disappeared, and you still have them in your prodigious memory. And the very easy question is, what was the letter that was here? Very easy. There were only 12 letters. Someone? L. Someone else, another letter? I take calls. O. Someone else? U. Okay. Good. Very close. I need one more. And we are done. No one plays? Okay. That's 3 players. We should have more. U, for how much? I take it.
10 euros.
10 euros. Okay, I'll take it. And you were?
1.
But for what? O for 1. L?
5.
5 euros. Okay. So I think it was L actually. We'll see it. It was L. Yeah, it had to be normalized with salaries. But you see, okay, so it was L. And so usually there is a bit more of gamers. Maybe we should shake up perception a little more. But you get a sense of what happened. First, it's difficult. Perception is much more narrow than we think, and we actually do run a lot of experiments in which we measure the performance as a function of the length it was presented, as a function of the position. We tend to attend more to the letters on the right than to letters on the left, as a function of the regularity of the letters. So Argentinians may have noticed, this is for you, Claudio, that there's a word here, which is bulo, which is a very suspicious word for, or maybe I'll let you explain later what bulo means in Argentina. So people tend to find this, and it's a word that's related to
something that is created that might not really true.
bulo.
Yeah.
Yeah, and it's
well, they have different concepts.
Yeah, you got it. Okay, now you got it.
That's right.
Anyway. So bulo is the apartment where you have your extramarital relations. Usually people have a house and they have a bulo. And the bulo is where they do the things that they don't do in the house. So some people, and so this in the end, when I do this in Argentina, is more like a psychiatric diagnosis of faithfulness. And this is the game. So anyways, but the point here is not so much whether people saw that or not, but by asking you, so for instance, you said €1. Of course, you are right, it has to be rescaled to the salary, but what you're saying there is I'm very unsure, or at least that's the way I would read it. Like, I'm not willing to bet a lot of money because I chose this because I had to choose it, but honestly, I mean, I'm very unsure. Some people are willing to bet their lives on this. They're really sure. They've seen, look at the one thing, the letters that appear here were the B, the U, and the O, sorry, the B, the L, and the O. This is very typical. People tend to, and it's very interesting on how perception works, which is that people tend to see in this location, the letters that were in other locations. So it was not like the Z or letters that were not here, not even like the Q or the T, but letters that were around. And sometimes these spatial swaps, which are unconscious, are actually very high confidence because people are really sure that the letter that was here was the E. So this leads to very high confidence errors. People make mistakes, yet they trust a lot the mistake they've made. This is something that happens and leads to obviously to errors in gambling behavior. So we could measure confidence, as we often do indirectly, by asking people to bet money on this, and how much they're willing to bet is a proxy for confidence. Or we can do something very simple, very naive, with the least technology that you've seen in your life, which is just asking people in a scale from, honestly, I had no idea, to I was completely sure. And the only thing they have to do is they move the mouse and they click, or even without a mouse, they just point with a pen and pencil, or pen or a pencil to the direction here. And what people are doing is they're expressing their sense of confidence, or the way we like to think is they're expressing their average or their probability estimate of the likelihood that their decision is right. So I made a call, and I'm trying to estimate what's the likelihood that the call I made was right or wrong. And people, when in general, there's a lot of psychological research on that, tend to underestimate this, to overestimate. So people tend to be more confident on what they've done than they should. This is the typical trend, but within this there's variety, which is what I want to show you here. So this is one subject that has done this experiment, not for one trial as it just did, but for 1,000 of trials. And those are the distributions of confidence. In some trials, the subject was very sure, so it responded 1, not too many trials. Some trials, the confidence was very low, and it leads to this bimodal distribution, which seems reasonable because the conditions of this experiment were close to a 50% performance, meaning that sometimes they were right and sometimes they were wrong. There's nothing fundamental about this distribution. If the task is very easy, it would shift to the right. If I'm asking you, like, what is 2 plus 2? 4, how certain you are? I'm completely certain. If it's a task which is completely impossible, it will be skewed to the left. The question is, how is this distribution compared to the relative performance that a given subject has? So this is one distribution. This is subject 1, subject A. Now, these experiments were done in Argentina, where we have a population with a pathology of confidence, as some of you may know. And so this is a more typical Argentinian, which is porteño. It may have sometimes a glimpse of doubt, but eventually it stays on a position of very strong certitude, right? This is how it feels. So this seems like a problem, and I want to place this up front because we're trying to understand how we construct confidence, and the first thing that appears is that I bring two different subjects, and they're completely different. So it's like pears and apples. How can I compare these two things? They have very different ways of expressing confidence. So what I said before is, and I think this is in the essence of biology, for at least one way of seeing biology, which is finding some regularities within diversity. Species are all different, but they have all genes, and they have all certain metabolic functions, and brains are different, but they have certain similarity. So the question here is not so much how these things are different, but where they are regular, and this gives a dimension in which I think we can do the science that we often like to do. So the question is okay, these two persons have their own language of confidence, and I'll go to that in a second, but is it really their language of confidence, or is something which is completely volatile, that will be different when we actually, if I make the subject come again and again. So we run this experiment, and we have these two subjects come on a second day, and they perform the same task, and they reported confidence, And those were the distributions of confidence. And then a third, fourth, fifth, sixth, and seventh day. And the point which you see here, I mean, you can do the math on that, but you don't need it, is that the way we express confidence is very idiosyncratic. We have a height. Some people have a lot of physical resistance. Some people are fast. Some people are strong. Some people have a high-pitched voice. And these are things that are very mechanical, so we are used to them. What I'm trying to show you here is that we also have a very idiosyncratic, persistent in time and definitory of what we are, way of how we express confidence. And this, I'm going a bit ahead in time, but this is in time in my talk. But you see how this is important for human communication. So all of you have gone to a doctor, and for instance, you tell the doctor, my bone, I have something wrong, and will it recover? Yes, it will. Well, are you sure? Yeah, it's quite likely. And the question is, what is the meaning of quite likely? Does it mean 72% probability that it's going to recover? Does it mean 64? We make a sense of that. But what you see here is that there is an issue of channels of communication. What for this person is quite likely is very different to what this person here is quite likely. And there's a lot of people doing actually practical applications of this, just trying to make people communicate probabilities in a more meaningful way, so that in many practical decisions that include judges, that include schooling, that include all medical consultations, that include when you buy a car and so on, people are speaking essentially the same language. Yes, thanks.
Two questions. One is,
yes.
So you're using confidence in many different ways, right? Because confidence is here in respect to something that is correct. In the first case, it's not something, it's confidence in somebody, but there is nothing correct or incorrect, right? So it's how you feel about it. So the meaning is completely different.
Yeah.
And second, what?
It's all completely different, but yeah, you're right. It's not the same.
It's not the same. I mean,
yes, not the same thing. Yes.
Maybe it's not going to happen.
Yes.
Or it has some probability.
Yes.
And the other thing is, well, maybe what is different here, I don't think that this is the case, but maybe what is different here is not the confidence, but is the knowledge of the guys.
Here there's no knowledge of the guys. This is in the task with the letters.
And that was for
this is in this task. But so I'll answer the questions now in a second. Yeah. So there was another question.
Yeah.
I'll take it and then.
I mean, whether you put more on the right side or on the left side, do you bear the consequences? Just imagine that you invest something and you get your money, or you earn more. I mean,
okay. So
is there any?
Yeah. Okay. Good. Two good questions. So first, the first one needs to be clarified. So I began saying confidence applies to a lot of different domains. Confidence of the future, self-confidence, confidence in the others. And then I said, but I need to say that again because it's not clear enough, I'm going to work in a narrow domain of confidence, which is the degree of trust that we have on the decisions we've made. And the reason we work there is because things are life is much easier in this particular subdomain of confidence. So all my talk is going to be confidence relative to a response that we've made, and we ask subjects to judge whether they are certain or not that the response is correct. And during my entire talk, except in the very end, this is going to be the only proxy for confidence we are going to be using. I'm going to sketch the idea that this difference, and this goes a bit to your question, that there is some transversality to how we express confidence. So people that tend to be very sure about their decisions also tend to be optimistic about the future, also tend to be self-confident on the actions that yet they have not made. And so this goes on a broader idea, which I'm going to only touch in the end of my talk, which is that there's a general sense of confidence, which applies. But in my talk, for like 90% of my talk, I'm going to apply it only to decision confidence. So the certainty that you have that the decision you've made or a response you've made, it's the same here, is correct or not.
Yeah, but for example, in this exercise, maybe you are very good at that. And you're able to remember everything, and then you could be there. So that could also be the case.
So that's why
the task is different.
That's why I also made this clarification, and all these are questions. And this is why we work on all these tasks at fixed levels of performance. So except for this one in which we allow some variability, all the tasks I'm going to show you here, we can calibrate the difficulty of the task so that subjects are at 75% difficulty. Performance, 75%. And the reason we do that is, of course, if you're at ceiling performance, then, which I mentioned before, confidence is very high, and this is trivial. If performance is very bad, then your confidence will be low. And we're interested in seeing what happens with confidence in the interesting dynamic range in which sometimes you're right and sometimes you're wrong. And in particular, and I'll go that in 5 minutes, the question we're interested in is where confidence can tell you. I mean, an ideal observer would be one that would assign high confidence when they are right and low confidence when they're wrong. This is a good gambler. And this goes to your question, which is how this translates to other consequences and other actions. In social decision making, this is obvious. If you trust someone, you'll lend them money, you'll give them money, you'll invite them to your place, you'll pass next to them without fear. If you do not trust someone, then you will change all this series of actions. You will cross to the other side of the street when these persons are there because you may wish that they will do.
But maybe
Here, in this task here, we can measure this precisely by, for instance, a gambling experiment. So how much we'll give you a pot of money, so you'll start with $100, and in each of these trials, you can bet either 1 or 10. And we'll do that, and what we see is that when we recover confidence from there, we get essentially the same distribution. So there is a strong correlation between an explicit report of how certain I am and an implicit action of the use of this confidence, for instance in gambling. In animal models, another very typical way of how this is used is waiting time. So for instance, if you're in a door and I'm waiting for a reward on the other side of the door, and I'm sure that it will be there, I'll stay 1 hour and wait for that. If I'm not sure, I have like a 10% probability, then after 10 minutes I will just run off. So in mice, the way we have to measure confidence implicitly, because they cannot tell us the confidence they have, is by asking them how much they are willing to wait for a reward. If they wait a lot, then they have high confidence. If they wait too little, then they have low confidence.
Yeah, but you could take instead a kind of risk aversion rather than confidence.
Yes. So this is the reason why typically we do not use gambling, which is that gambling actually has two components. One is the likelihood that you think that you're going to win, and the other one is your risk aversion. So even like if it's a very high bet, even if you're very sure, you may opt out of it just because you have risk aversion. So they're very similar, but they're not exactly the same. And part of the reason is that gambling is filtered by risk aversion, which is the reason why we prefer doing that. But still they're very correlated. Yeah, so those are the technical points. Okay, so now the question is I showed you one subject has a way of expressing confidence, and it's very similar as days go on. And then a question which also came in the questions you were asking is whether this has some transversality, whether this will be a property of this subject or is a property of this subject in this specific task. If it's a property of this subject in this specific task, then it's not so interesting. And so what we did is this was like a long experiments in which we have subjects doing different tasks for different sessions. And so you have now 4 different experiments. This is and they have different modalities and different type of decisions and so on. So for instance, this is an auditory experiment in which it's like tuning a guitar. So there's a tone, and then there's a second tone, and the second tone can be high pitch in the first one or lower pitch, and the subject has to respond which of the two was the higher pitch, the first one or the second one. And this task can be made more difficult or easier by just changing the difference between the two tones. If they're very far away, it's very easy. If they're very close. And what we do is that for each subject, we fix this number so that there is 75% of performance. So we keep them at the range in which performance is the same. This is a very similar task, only that instead of comparing noise, it's comparing luminance or contrast between two ratings. This is a task in which subjects have to, it's more like a voting task. So something is fluctuating in time, and they have to incorporate all this information, and then at the end of the trial, they have to respond whether the average luminance was greater on the left. There are different tasks. You can go in detail, but essentially they sample. One is dynamics, the other one is static, one is symbolic, one is perceptual. They range a wide variety of parameters in decision space. And then what we do is we measure this distribution for each task, and then we measure different estimates of this distribution. The first one is, of course, just the mean. So the question is whether people tend to be they are performing always at 75%, but the question is whether they are very sure or they tend to be very unsure, and whether this is something that's transversal across tasks. And what you see here is, for instance, this is almost the same data I showed you before. So it's each dot is one subject, and what you see here is the confidence, average confidence on day 1, and average confidence on day 2 in the auditory task. And you see that the subject that had very low average confidence, this was I was going to say Brazilian, but not. Of course not Brazilian either. It was maybe, an Uruguayan. And so they're here, and this is, Brazilian, very high confidence on day one, but in any case you see that average confidence in day one is very expressive of average confidence in day two. This is not different from what I showed you before, but this is now different, because what you're seeing here is the average confidence in the auditory task compared with the average confidence in the contrast task, and this, you can follow the whole matrix. And the point is that all these things correlate quite tightly, meaning that if a person tends to be very confident in one modality, in one type of decision task, they also tend to be very confident in tasks of very different nature. This is the result of all this summary. Now, we can measure many more things of these distributions, whether they're by model or not, whether they're skewed, and they tend to be very reproducible, but the one thing I want to mention, the one most important thing, because this is actually the essence of what we try to find, is, and I sketched this before and now I can say it again, is the capacity of confidence to tell right or wrong. You can think it as a casino player. A good casino player is one that when I think I have the good hand, I'll bet a lot of money and I'll win a lot because I was right. If I have a good sense of probability, a good sense of confidence, I'll be winning. If I bet very strong because I'm very certain when I'm wrong, then I'm a bad gambler. And you can extend this idea of the casino to life. A person that assigns good confidence is a person that understands that they are right when they are right and that they are wrong when they are wrong. A person that assigns confidence very poorly is a person in which the distribution of confidence is not very different in the right choices than in the wrong choices. And for this I'll take just like 5 minutes to give you a pedagogical description of this. So in this distribution here, it's an aggregate of 1,000 responses, some of which were correct and some of which were incorrect. And now we're going to separate these distributions, and the question is whether the distribution of confidence in the correct responses is to the right and the other one is to the left. This would be a person with a precise sense of confidence, or whether they are not. And to do this, we do it in this way. The problem is that these distributions are not parametric, so we do a non-parametric way of doing this, and I'll guide you through this, just in case. I'm sure a good part of you will know it. The way we do that is measuring the receiving operating curves. So this is a sketch, and it's the pedagogical part of this talk. I mean, and I think maybe you'll take something interesting from that, especially if you don't know this. So this would be a person that I call a person with a calibrated or a precise sense of confidence. They have a distribution of confidence which is low in the wrong trials. This is blue. And they have a sense of confidence which is high in the trials in which they were right, in which they were correct. Here, the subject will gamble strong and will be right on doing so, and here it will gamble low and again will be right on doing so. The point is that you can use confidence to tell right from wrong. This is the distribution of a subject that has a very lousy sense of confidence. Sometimes they're very confident but they were right, sometimes they were very confident but they were wrong, sometimes they were right but the confidence was very low, which it shouldn't. And these two distributions cannot, if you use them as a classifier, you cannot use them to actually know whether the subject was right or wrong. And so the question is how we can tell apart this from this. And there are different ways in you can do that, but of course here the problem is that we know nothing about the particular shape of this distribution. So we do this in a non-parametric manner, and this is very standard. Again, and many of you will know it, but again, I won't spend the 5 minutes explaining this. So what I'll do is I'll move a line here, and if the two distributions are separated, this line will first cross all the blue curve, and only then start crossing the right curve. If they are overlapping, it will cross the two curves at the same time. If it's a really bad subject that has actually higher confidence for the wrong trials, then actually they will be separated but in the wrong side. And so this is how it goes. You start measuring how much of the distribution is to the right of this line, and then you start moving this line to the right. It begins with the blue distribution is all to the right, and the red distribution is all to the right, so you're in this point here. And as you move to the right, you start crossing part of the blue distribution, and so you move in this line as you go in this parameter. This is a continuous parameter, of course. And then you go in this line until you hit this line, until you hit this point, in which you start crossing the red line and you go down on the other axis. So what you have here is that you have a very large area, maximal area, under this curve compared to the diagonal. Instead, if you cross both of them at the same time, what you'll start doing is that as you move this line, you start going, actually if they will be completely overlapping, you go down in the diagonal, which will be the minimal area. And so you get a curve like this. So this is standard decision theory criterion, and it's something that has many, many years, and many of you surely know it. But measuring this area with this parametric technique is a way of asking the question of how separable are these two distributions. And how separable are these two distributions is a way of asking the question we wanted to ask, which is how precise is the sense of confidence of this person. So a very large area would mean that the sense of confidence is very precise. A very weak, a very low area will mean that the sense of confidence is very unreliable, it's very imprecise. And now we can measure this. It's the same sketch that you saw before, except that here you don't have actually the average of confidence, but you have the precision of confidence measured in the way I just showed you now. And again, you see that this correlates, although the correlation is not as strong as it was before. And actually, in some across, it's not significant in many of the cases across tasks, although it's always positive, which is, or almost always positive, which is what you see here. So the summary is that across tasks, the average value of confidence is tremendously stable. The precision of confidence, the capacity of a person to know when they are right and to know when they're wrong, has some stability, but not as much stability as in the other case. And if this is the case, and this will be the last slide from this part, if this is true, that people do have a sense of a precise sense of confidence, we can ask, what is it about the brain function of the people that have, we can rank people based on these. Some people have people that are here have a very precise sense of confidence, people that are down here have a very unprecise sense of confidence, and we can ask, what is it about their brains that distinguishes the one from the other ones? So this is what we did. We got subjects in the scanner, and they lied in the scanner doing nothing, because we're measuring resting state activity, and we measure the correlations and the fluctuations of resting state activity.
Sorry, which scanner?
In an fMRI scanner. What type? It's a 3 Tesla.
No, well,
An fMRI. Yeah, fMRI, yes. But the point is that in the scanner, the subjects are not doing this task. In the scanners, the subjects are just resting. And we measure, while, I mean, again, I imagine this is a broad, you let me know if this is very obvious, but I prefer to explain these things because I think they will be here the people that will not know that. So essentially, when you record from the brain, you have like 60,000 voxels typically in fMRI. They have a lot of spurious local correlations, so you can coarse grain that, and typically people have done that. There are many ways of doing that. Essentially, you get like in the order of 150 temporal signals. And so you have one part of the brain, another part of the brain, and another part of the brain, and now each of these regions are big chunks of the brain. They are like regions, like the occipital cortex or the parietal cortex. So those are large brain anatomical structures. And eventually, in resting state, you can ask for, so you may have things like this. You will have two signals that actually spontaneously have the same type of pattern. So those two regions have a relation, they're correlated, and so you can build a network or a matrix in which you measure the degree of temporal similarity between these different signals. And okay, so this is the part. This is the more complicated part of my talk, but I want to make it precise. Okay, so this you can do, and when you do that, you get a matrix. And this matrix is a matrix of about, again, 180 times 180, where each of these is a brain region, and you'll have regions that are correlated and other regions that are like you get a matrix like this, where some of these regions are correlated, and this is for one subject. Okay? Now you can do the same thing for the different subjects. You can do this for another subject, subject number 2, and subject number 3. And you get the correlation matrix for subject number 1, subject number 3, subject number 3, and so on until subject number 30. And now I'm going to do a plot here in which this is what I'm going to run. I'm going to measure the psychological variable of my interest. In this case, it's for example, the precision of confidence. So I'm going to rank my subjects here by precision of confidence, which is ROC curve. And here, I'm going to take one voxel, like this voxel here, and I'm going to take the connectivity of this voxel for each subject. And I'm going to plot that. And when you do that, you find some voxels in which the strength of these connections, the strength, for instance, between the parietal and the occipital cortex, is not explicative, does not correlate, is not informative of this psychological variable that you are studying here. And you'll find other regions in which the strength of this connection for different subjects varies on a way that it can explain the psychological variable that we want to study. So you'll find a relation like this, a strong correlation between a psychological variable and the strength of a connection. And this is what these maps here show. So what you see in each of these maps, and they are very dense, I'm going to explain that now in a second, is whenever there is a link between two regions, it doesn't mean that these regions are connected. It means that the strength of the connection of this region increases as we take subjects with a more precise confidence system. Okay, so that means that if I were to look this connection, the strength of this connection is informative of a psychological variable that we want to study. And what you have here, and this again had been done many times before when we did this study, is that by having subjects at rest, you have, and I'll tell you in a second what each of these three graphs are, by having a subject in the scanner and by seeing the strength of specific connections, you can predict the performance of these subjects in a visual task. This is what type 1 means. It's the performance in the task of the letters that I showed you before. So subjects that have the occipital cortex, which is the visual part of the brain, which is connected to other systems of the brain, when these regions are more connected, these subjects tend to be better in a visual task. This was not a great surprise, yes?
This is not the type of research that now they tend not to do, because random correlation can emerge if you study 10,000 peoples.
I think this question is wrongly placed. And I'll tell you, if someone tells me that there is a research that I cannot do, then I will do it.
Yes, but you have to
This is my first reaction. So I will rephrase your question, and then once I rephrase your question, I will answer it. So what you're saying is this, as many other research, is one in which you should be careful and do the right statistics so that the results you find are not spurious of doing actually too many statistical tests, but actually have been compensated so that you find reliable results. And this is not for this research, but this is for research in general, for all types of research. I'm the first skeptic and critical, and I've written papers on this. And actually, it doesn't go. Part of this, I told you, we downgrain this to 120 elements, and then we do so we can go on the details on actually how we find these correlations to be reliable to the multiple tests that you can be doing. But the sole claim of saying this is a research that cannot be done to me seems at least
I'm
quite
not in
strange.
this field, but I heard that in psychology now what they want is first you say I will do a study of this, and then you see the correlation exists.
Yeah, but this is the case. This is the case. Here we had a hypothesis. So here we had a test, which is what I'm going to show you. Actually, this is just a replication, which is quite healthy. We had this paper. This has been replicated in many studies, and this is not what I wanted to show. So this is just in terms of there's no novelty here. The novelty will come right now in a hypothesis which we had, which is the following: the subjects here are doing 3 different tasks, which I didn't tell you now. Again, this is the more complex slide, and then we'll go to very simple slides after this. This requires attention because there are many variables here. So those are resting state fMRI in the sense that we are not showing subjects to do like a visual stimuli and we see a facet response to that, but we see stationary correlations. But we did them in 3 different states, and 3 different states of attention. One state, subjects did what's called in fMRI resting state. It's a very ill-defined state in which you tell a subject, just do nothing. Like if you're in the elevator, you go there, you close your eyes, and you have random thoughts emerge. But of course, the random thoughts that emerge are very different from one subject to another, so it has issues. But this, again, has been a long industry. Here, same situation, same scanner, no stimulus. We ask subjects to concentrate, to drive their attention to the sound of the scanner. So the scanner, if you've been in one, it's like, makes a lot of noises. And we ask subjects to focus their attention on the outside world, on the sounds and on the noises of what they're hearing. In this case here, subjects again stay for 15 minutes, and we are subjects to concentrate on the respiration. Here they're breathing, here they're breathing, here they're breathing, but here we are subjects to direct their attention to their respiration. So you could think it as a, I don't even want to use the word meditation, but you could use it as concentrating on internal states. And we had one hypothesis, which came from studies which were done before, which was that this state, which is called interoception, is driving the mind to internal states of the body, should be similar in structure to the state of introspection, directing attention to our own thoughts, to our own knowledge, to our own probability distribution. So you could think that, and this is again just a metaphor, that measuring confidence is looking within the brain to the information that I have to accomplish one task. Doing interoception is looking within the body to actually understand and feel the senses and different. So we had the hypothesis that actually, when we did not measure visual performance, but the capacity of a subject to have a good sense of confidence, this should be revealed in these states, but not in the other states. And this is exactly what happened. You see here that that we measure 3 brain networks, and we make one in state of interoception, endogenous attention, exogenous attention, and neutral attention. So attention just not directed explicitly anywhere. We measure the connections, at the different connections. We measure whether the strength of these connections can be predictive on how well they will do in a confident task, and we see that there's this relation here. And actually, if you run, typically you have many different ways of actually solving the problem that you mentioned, which is the problem of that you have too many tests that you're running at the same time. So if I run 100 tests, 5 of them will be true at 5% by definition. So this is part of the problem. So you have to compensate that. One way, which is a very healthy way of compensating this, is by doing cross-validation. So you train your data just on a subset of the data, and you say, well, now I have a model that on a data which I have not fit, I have not used, I should be able to predict whether these people will do well or not, and you do that only for one model. So no multiple comparisons there. You have your model, and you say, this model should be predictable in subjects that I have yet not explored. And when you do that, you get very high levels of classification, saying close to 70 or 75% of actually capacity of saying, you look at the brain of someone, if this person is driving the attention inwards, you can tell whether this person will have a good sense of confidence or not. If this person is driving attention outwards, then the capacity of your classifier is very low. So again, what this states is it gives experimental support to an idea that was floating before we ran this experiment, which is that confidence, the capacity to think about our thoughts, to think about our knowledge, is intrinsically related to the capacity of looking within us, looking within our respiration, looking within our hearts, looking within our bodies. Okay. So this section I'm going to skip because it's a very technical one.
So Mariano,
yes.
So does it mean that if you train
yes,
your attention,
exactly. I don't know. So this is the natural experiment, and we've been wanting to do this experiment. Yes, this is the natural hypothesis. Sorry, I'm going to finish your sentence. What I guess you were saying is that if you train your interoception, so if you train your sense of looking within you, then you should increase. This would be the causal relation of an intervention. This experiment has not been done. It's a difficult experiment because training these things is quite difficult. It takes a lot of time and
But you just take different subjects.
yeah, no, you could do it.
Few of them are
It's a completely good experiment. It's just an expensive, a temporarily expensive experiment, and we didn't manage to do it. But yeah, it's been the one experiment that we've been wanting to do like for the last 5 or 6 years. Okay, so I'm going to skip all this section, which was more on physiology, and I don't think it's really needed here I'm going to skip all that. And I'll tell you the conclusion of this data very rapidly. So I'll go here and I'll tell you what the result is. And you can just go and look at the paper if you're interested in this. If not, you trust me. And so this is the result which we got. Again, I saved 20 minutes of my talk by not presenting exactly how we reached this conclusion. So I'm going to present it just to move to what goes on through that. So what we did is we ran an experiment in which the fluctuation experiment, light fluctuation experiment, and so there was like fluctuations of light in this side and fluctuations of light in this side, and the subject had to answer whether this was brighter or this side was brighter. Very simple decision task. And what they have to do is just an average of luminosity. And what we found is that to actually make the decision, subjects do that, so that they calculate the amount of, they almost calculate the amount of luminosity here, except that they don't take all the samples into account. They only take the first samples. We do that by doing backward regression based on the choices that they've made. But what we found, and this experiment was very controversial, and so we've done it many times. This experiment I've done more times in my life, actually. And is that, how many of you are biologists here? No, excellent. I'll tell you, neither I am. When I went to Rockefeller, this was an institution of a biomedical institution, so it was the Center for Physics and Biology where I was. And there I heard something that actually gave me a very weird lesson on the epistemic difference between biology and physics. I was in a table where they were speaking about the results of someone, X, and say, X must not believe this result because he only published it once. You know, so the idea that if you trust something, you should publish it many times, and the idea that the conviction of your data is the amount of papers that you aggregated on. Again, how we construct validity in science is something that we will discuss for a long time. Anyways, when we looked at so for choice, subjects do what they have to do. They count the amount of votes here, they count the amount of votes here, and they subtract them. This is what the task asks for. But for confidence, they do something different. They only count the votes of the choice they've selected. So if they selected right, and there happen to be a lot of positive fluctuations in the right, then their confidence is very high, even if there also were a lot of positive votes on the left. No, they're not doing the difference, which is what they should do, but they're just counting the positive votes in favor of what they made. And this was a quantitative replication of something that Daniel Kahneman, the Nobel Prize in Economy, had discovered as a principle on a strong heuristic on how we build confidence, which he named confirmation bias. It's the idea, and it's going to be the guiding thought from now and to the 20 minutes to the, how much time do I have?
15 minutes.
Okay, so in the 15 minutes to the end of my talk, which is that to make decisions, we do not sample the evidence uniformly, but we bias the information we choose, and this actually ends up constructing or generating a completely distorted but reliable sense of confidence. So this is the first principle. The second principle that Kahneman found, and again one which we replicated in the lab, or which we quantified in this kind of decision, was the following. It's clear in this example. So Kahneman made a lot of these experiments like this. He gave like something like, in a telephone poll of 300 seniors, 70% support the president. So we're all used to this, forecast, electoral forecast, and this is typical. If you present this to someone, and then half an hour after you said, what did I tell you half an hour ago? Then people will say, well, you told me that 70% of the people support the president. And you may think that it's the same, but it's not the same. What I missed was the fact that it was a poll of 300 seniors, which is very important because this speaks about the reliability of the data. Actually, if instead of saying that, I would say a poll of 21 million people said that 51% of the people support the president, this is more data in favor of the hypothesis that people support the president than this fact. Yet people ignore that and just take this number, ignoring the fact, and the other typical cases that which I think you will all recognize is the following. Imagine there's a bag with 3 million balls, and you take one and it's red. You take the second one and it's red. You take the third one and it's red. Fourth one and it's red. The fifth one is it's red. I mean, it's obvious that it's red. But what we're forgetting is that it's 4 points out of 3 million. So we have no idea what the fifth ball is because we have not sampled 2,900,000 balls. Okay, so the question is, how does this work? And for this, again, we wanted to build something which was amenable to trying to understand the mechanisms by which this is done. And this is what we thought of. We said the following. It's a bit of idea of what if, again, in your jargon, maybe confidence is built as a stochastic resonance process, in which maybe it's injected or inflated by noise. And so this is what we did. Imagine that you have a decision problem, and the decision problem is whether something is moving to the right or to the left. Actually, this is the decision that I'll show you, which is you'll have oriented bars, and the question is whether these oriented bars are tilted to the right or are tilted to the left. And in these three cases, they're actually tilted to the right. And the average value of tilt is exactly the same, but what changes between these three is the amount of noise that there is. So the average of the distribution is the same, but it gets noisier and noisier and noisier. And the question is what happens when we have noisier distributions of probability for a given task. So this is what is represented here. Now you have two distributions. It's a sketch of the internal probability distribution for the task I just gave you. And so you can see here that the correct response for this is to the right, because it was tilted to the right. This is the internal distribution, and you can imagine that you sample one randomly, and all the ones that you choose from these sides are errors, because if I happen to choose a very noisy sample that was tilted to the left, I'm going to erroneously respond that the on average was tilted to the left if I do a one sampling for the averaging. And so as I increase the noise, the task becomes worse. Performance becomes worse. And this is something that people have done for years and years, and we repeat it, and I'll show you in a second. That's exactly what happens. Now the thing is what happens with confidence. And with confidence, you should do a statistical judgment for that. But if instead of that, people are just taking random samples from here, and if these random samples are big enough, this is another criteria of confidence, which is more based on what Kahneman just showed. Like saying, I picked one random sample from this side, and it happened to be 80% tilted or 90% tilted, then I have very high confidence. Then you have this seemingly stochastic resonance, in which you see that by noise, you're increasing the likelihood of crossing the barrier of high confidence. And then there's a very paradoxical hypothesis, which is that as I make the stimulus more difficult, because I increase the noise, subjects will get worse and worse and worse, but their confidence will get higher and higher and higher. So very irrational. We are doing worse, but we think that our confidence is worse and worse. So here you can see it actually in this, so let me show you how this would be. Again, here you have the three green, red, and blue. They correspond to green, red, and blue. And what you have here is the performance as the average tilt increases. So as the decision signal gets greater and greater, performance increases. But as the variance gets greater, from red to green to blue, then performance gets worse and worse and worse. This is the expected theoretical curve for how performance should be in a task like this. And then you have two different ways of building confidence. One is the normative one, where you just do the statistics, like a standard deviation of this distribution, the likelihood that I have of being right or wrong. And as the noise increases, which is the case here, if you have a normative model for constructing probabilities, then performance is worse and confidence should be lower. So it's a reasonable model. If we have a model that's just based on the signal, ignoring the reliability, ignoring the fact that I'm just taking random samples, then there's this paradoxical, again, noise-driven effect by which subjects have higher and higher and higher confidence. So you see higher noise leads to higher confidence. So the predictions for performance are the same for both models, but they're completely different predictions for performance for a stochastically driven model or a normative model. And so those are the predictions. Again, signal plus noise. This will be the normative model, and this is the stochastic driven model. And you see that this is exactly what the data shows. So we do show, again, a very irrational, but very reliable and understandable way of how we construct confidence, which is that when we are sampling just a piece of the distribution, and as we increase the noise, the likelihood of just sampling a random part gets higher and higher, which is what I sketched here. So subjects, when they respond to this task, they do not see all the bars and make the average. What they see is that like 5 or 6 bars, they're sampling a subset of the distribution. They commit to the right, and they're very highly confident because they ignore the fact that they have not looked to the other 3 million balls, which is what I'll show you now in the last 5 minutes, also happens to a high degree in ideological or political questions. So this is, and actually we ran a second experiment in which we asked subjects to draw the line or the circle that they thought they had looked more. So here I just drew it manually, but we could do that. And when we try to predict confidence, we can predict confidence very well as the normative view of a subsampling of the distribution. So subjects are optimal and they estimate the variance correctly, but not of all the data, just of part of the data. And this is the one thing I would like, yes.
I think you would pay attention to the place where it's less density of bars, because there you can distinguish better if they are more tilted or less tilted.
Yes.
If you go to a mass of bars, then you don't see.
People do that. So that, yeah, so the way people typically solve this task is that they look for outliers. So this is changing, of course, with time. But suddenly there are 6 bars that align the same way, and this pops out, so you look there, and then you commit to the left. But again, you are ignoring the fact that there was a lot of information that you're not using to commit your confidence. And so in the last 5 minutes, I would like to move to something which I think will be a bit in line with people doing here things which are more related to the quantitative use of the social sciences, which I also do a lot, and which was not the focus of my talk today, but I would like to connect to that on this idea of constructing confidence based on normative views of partial information. So we ran this experiment in which now we as subjects also whether something was correct or it was wrong, but it was in domains in which there is not a ground truth, in which there is not, so for instance, we asked questions about abortion. So this was a question of a woman that has a pregnancy of 5 months old and decides to go through abortion, and the question is whether what she did is right or wrong. And you see that in our population, 60% of the people thought that it was right, and of course this depends a lot on parameters. So there's nothing fundamental on that. It depends on the number of months people thought why she didn't do it before, and the right of doing it. And if we would change this from 6 months to 8 months, then it would move to the left. If we change it from 6 months to 2 months, it would move to the right. Exactly where this is here depends on many parameters of how we phrase the question, and it's not what's relevant for I want to tell you. This is a question, this is a very interesting question. It's 2 brothers, 2 siblings, that decide to have sex, protected sex. They like each other, they're adults, it's consented, it's completely consented. They do it one time, and the question is what they did is right or wrong. And people split very strongly here. Some people think that they are adults and they're in their own right of doing whatever they want, and some people think that it's just wrong and it cannot be done. And so again, what we ask people is to respond this in a scale from 1 to 10, where 1 means it's completely wrong, and 10 means it's completely the right to do that. And then there are questions like, for instance, this is a whistleblower. It's something that has a lot of acceptability in Argentina, so it's defending French, it's the tension between friendship and the law. So this is the situation of someone that comes and did an infraction, but really didn't want to do it, and it was an accident, and he's really desperate, and he wants to run away from the country, and then the police comes and he asks the person that's hosting, the one that did the crime, whether the person is there or not, and he says, I don't know where he is. So he's defending friendship as opposed to protecting the law. The question is what they did is right or wrong, and you see that in Argentina people think that this is right. This is this is like the problem of Ex Machina, if you saw the movie Ex Machina. So the question is it's a machine that for all what you can tell has feelings, and has consciousness, and the machine tells you, please do not stop me, I will cease being what I am, but the procedure says that they have to do it, so they turn it off, and the question, so you see, it's questions about morality, where people spread between right and wrong. And I'll skip this for a second. And so the point here is that you see this distribution, and here what you see is complete inacceptability. So that means that on average everybody thinks that it's completely unacceptable. Here it's complete acceptability, and here it's 50%. And this 50% may come for 2 different reasons. Either everybody thinks that it's okay, not completely fine but not completely wrong, or it can be because some people think that it's completely right and some people think that's completely wrong. So you can reach 50% of consensus in very different ways with very different degrees of polarization. When you draw this data, you find a pattern that was predicted and theorized by a very famous psychologist called Coriat, which is the following argument. The argument is that when we construct confidence now in social domains, which is more difficult than the one I showed before, what we do often is we look at the other people. And when we look at the other people, we think other people as random samples. And so if all the people say it's 100% correct, then I should be very confident because there's a lot of consensus and essentially there's very little dispersion. If I see that there's a lot of, so essentially it's doing social statistics as a measure of consensus. And this works very well for questions about facts. For instance, if I would ask, is Brazil larger than Luxembourg in area? Everybody would respond yes, 100%.
and everybody will be very confident. And confidence reflects the fact that everybody thinks the same. So people have consensus, and this consensus is reflected within each individual in the confidence within. If it would be a question like, is Australia larger than Brazil, which is a difficult question, then the people will be split, consensus will be close to 50%, and the confidence of each individual would be very low, because it's a difficult problem, so people respond differently, again, because assuming that people are independent samples. And so this was a theory that explained a lot of the data for a long time, but there was something very clear that could not explain, and it appears here in this experiment, which is that, so this is the Coriat line, and you see that many problems, this is not a fit, it's just an illustration, you see that many problems lie in this line in which, as people get more consensus, so there's more agreement, this means that in a way, we all think in the same way about this problem, and so if we would run statistics on people, we can predict individual confidence from social, from social confidence. But there are some questions, like siblings here, like abortion, there was where you see that actually confidence is extremely, is above what would be expected by the level of consensus. For instance, this question of siblings, consensus is very close to 50%. It's a very difficult question, yet people tend to be very confident, ignoring the fact, each one ignoring the fact that there's half of the people that respond differently from what they think, which is something that again, I think is very typical in our theories, recognized in our political scenario. So, again, the model, and I'll sketch this in a second, is that instead of doing consensus, again, it's the idea of polarization, is that you can, the idea is that each sample is not comparing to the entire distribution, but it's comparing its value to the cutoff line. So if I am at 0%, I'm asked about siblings, and I think it's completely wrong, I am far from the midline, and so my confidence is very high, and if I think that I'm completely right, so I'm standing here, and again far from the midline, and my confidence is very high. So this is very similar to what we saw before in the very simple problem of orientation, in which each different individual is solving the data on a different dimension, on a different subset of the data, and is making conclusions on that, ignoring the fact that the data set is larger than the other people may make confidence on that, may make predictions on that. And this is the predicted confidence based on this model. It's a model in which I don't use consensus. The only thing I use is my value relative to the decision border, to the 50% border, and you can see that this explains to a good degree the data, including the polarized and the non-polarized questions. So this is a much better fit, actually, than just assuming that people assign confidence through consensus. And with this, I want to thank people, which they are there. Luciano Paz may, well, he did the work on the part that I didn't show, but hopefully he'll be at least listening here, and then all the other people that are here on the different parts of the story. Thank you.
Comments or questions? Yeah.
How reproducible are these brain scans from day to day?
So the brain scans, we did not do it day to day, which would be something desirable. Other people have done that with very similar analysis, and these matrices of correlations, and we've done that not in this experiment but in other experiments. And these matrices of correlations for one specific subject, they're also they're quite reliable. So the matrix of, they're quite reliable. Now, one thing is that these matrices are correlations on long time scales, in the order of 15 minutes. Typically, these experiments are run between 8 and 15 minutes. First you have to think that this is a very low temporal sampling technique, so sampling time is close to in the order of a second. But you can break down these 15 minutes in smaller windows. And when you do that, you see that this matrix of correlation, which is the average correlation, actually breaks down in different states. So it passes some time, it's the aggregated result of actually different stable states. And actually, the lexicon of these different states, so the number of states and the type of states, is quite typical across one individual. So if you do an individual and you come back on the next day, then the type of states that you will find will be very similar, but they change
with mental content. So for instance, they're very different if you're asleep. Actually, the number of states decreases. They're very different if the person goes through anesthesia. What happens there is actually that the correlation in the matrix becomes very trivial and becomes almost completely explained by the anatomical structure. So it's the trivial connectivity of just the white fibers in the brain. And you get different number of states, but increased states if you use drugs like psilocybin or LSD, like psychedelic drugs. So essentially, in a normal state, one person will have quite reliable and reproducible states, but you can pharmacologically change the state of the mind so that you...
What happens if the fast and the slow process are in contrast? Do you have a
fast and slow meaning?
Like when you have the three phases. I actually, for my first instinct was I picked the middle one because it looked like cleaner. And then with more reasoning and thinking of the people in my life, I arrived to the decision that...
so I mean, there's an industry of research on that. There's a very famous paper, that's one that's actually quite controversial. So I'll tell you the result and then you can go and dig on that, whether you think that it's right or wrong. And so it does essentially the kind of experiment you're calling for. So you have to make decisions, and either you have to make them very rapidly, like in 500 milliseconds, or you can think them for a long time. And what they change is the dimensionality of the decision problem. So for instance, the decision can be a decision about the length of a bar, and then it can be about the length of a bar, but also the width, but also the intensity, and also whether it's curved. And you have to make a function, you have to optimize an implicit function of 1 dimension, 2, 3, 4, 5, 6, 7 dimensions. The result found in this paper is that for decisions which are low dimensional, if you think them longer, this is natural intuition, so you give more time to think about them, then performance gets better. So thinking more about the problem. And the surprising result is that for high dimensional decisions that involve many dimensions at the same time, rapid responses are more accurate than thought and slow responses. And the theory for that, so it's not just a paper, it's several papers, and it's more likely partly true. It's probably not completely true, and again, it's hard to say because it's a domain in science in which there is a lot of controversy. The idea is that slow thought is conscious thought. It's typically fueled by language, so you think about it in a linguistic way, you're aware of it. And one thing that we know of consciousness is that it's very narrow. You can hold a number of things like 3, or if you try to hold numbers in your mind, you hold 3, 4, 5, 6 maybe at most. But if you just open your eyes, you can see 50 different things. So the idea is that the conscious mind, it's very narrow, and so when you have many dimensions, you're focusing on a small number of these dimensions, and so you make mistakes because you ignore all the other dimensions. So a low resolution system that can deal with all the dimensions at the same time leads to better responses than this would be the average, the rapid summary of, again, a controversial long line of research.
And with the confidence of this,
confidence changes in time, and this we do many experiments in which you can probe different moments of confidence and you can ask how it fluctuates on time. It's built on time, and actually confidence uses post-decision information. So once you've made a decision, and this is very typical in a lot of decision making. For instance, we study chess players. Chess players, when they make a move, especially in slow time controls, before making the move, they annotate the move. And in the moment they annotate the move, many times the expression of this action allows them to see an error that maybe they had not seen, and so they start doubting on the decision that they've made, and eventually they change it. So it's something that they use in their advantage. You think writing it down takes time, but it's some form of preview where you've made the decision, but then after making the decision, you continue processing information from a different perspective, and this changes confidence in the decision. This is very typical in a doctor. I mean, when you go out of the doctor, most of the people keep on ruminating, saying, did I do right, did I do wrong? So we keep on updating confidence long time after we've made the decision for which this confidence was relevant. And this is used, as in the case of chess, but also many other decisions, for what people describe as changes of mind. So eventually you may come back and say, you know what, I don't want to have surgery. So all this work that you had, sometimes it goes on to changes in action.
Yeah, Damian.
I think you mentioned that by the brain scanner you can predict the level of confidence of. So if it is a good, how you say,
precise,
is it
calibrated, yes.
Exactly. So you didn't comment on the consequences of that, but do you think we go to, as we get to know the brain, how it works, we go to the point where, let's say, corporation were to have hire people or something,
Yes.
scanner, and whether you get that score or not, you get.
Possibly, but this goes also on the direction of the question. People do that all the time. So when you ask, for instance, people in human resources, people hiring people, I mean, there's a lot of research, investigate everywhere. When people, without these techniques, people make decisions in 300 or 500 milliseconds. The person hiring the employee has made the decision, typically based on things that are not the things that are relevant for the job, and they're relevant like to the face that the person had, the smile that they had, whether you think that there is feeling or not. So what I'm saying is that there's a lot of unfairness in human choices, in human to human choices. This goes all the way to judges. I mean, there's many judges are professional decision makers, and there's so many experiments in judges saying that you present a judge a case, and the same case, and you just change the face of the person being trialed or of the person that was the victim. And as for instance, when the person that was the victim becomes closer to the judge, in racially, even in shape, form, then the judges become more harsh. And the other way around, as the accused becomes closer in proximity, they become being less harsh. So what I'm saying is that humans have been in all domains of human judgment very unfair to other humans, and I don't think that we need this technology for this to be a risk. I think it may be the other way around too, in the sense that understanding all these biases that we have, understanding that we have this irrationality when it comes to making decisions, when it comes to assigning confidence to ourselves, to things, or to other people, is a way to changing that. And this actually happens. In the United States, there are trials for instance, what I was just saying to you, something that most people recognize, which is it's called empathy. So empathy is supposed to be a very good feeling, but empathy has a problem, which is that you feel empathy for some people and you do not feel empathy for other people. And so the principle, and typically, we know for whom we feel empathy. We feel empathy for the people that look like our children, our close person, and those people that physically resemble or could be them. To some animals, we do not eat dogs, but we eat cows, something that has absolutely no rationality other than the social relation. I mean, all the way around, the notion of fairness changes. So in the US, and I think this is very right, there is a treatment for de-empathizing the judges, so that they reach something which is desirable, which is that they treat everyone in the same way, regardless of whether they raise an emotional feeling or not to the judge. So
maybe you have to subtract the average there. Eh? So take only the fluctuation with respect to some average of empathy or something like that.
yes,
because taking absolute values, you can make mistakes.
Yeah, but the issue is a very biased and narrow notion of proximity. Again, I think that the principle which we all share, which is the principle that does not hold in any decision system from humans to humans, is equality of rights. This is not true in almost in any domain.
Okay. Last question. Who?
And sorry, but it's quite technical, but I was interested in how do you tune the ratio with which you predict right or with which you remember right the letter to 75%? Because
no, that's the only one. Yeah. So this you could, because you could the critical variable there would be the amount of time between the presentation of the letters and the presentation of the cue. There's something because what happens there is if the cue is very close, you see them all. And this is called iconic memory. It's a visual buffer where for 200 milliseconds all the information is in your visual cortex. But this information fades down very rapidly. So if you ask the same question about a second later, then it goes down to the limits of working memory, which is close to 2 or 3 letters. So we could, but in this particular experiment we did not. So I mentioned that we fixed performance for all experiments except for the iconic memory experiment, in which performance varied, but not a lot, because subjects were. This is why we could do the first thing of measuring what brain patterns predicted performance on the visual task, because performance was not the same. If performance were to be the same, then we could not do this.
No, like, yeah, the actual question was not really how do you tune it, sorry, but when you tune it, how stable is the tuning? Because when you tune it in other tasks, and then they can still get better or worse.
It's not perfectly stable. So you dynamically, so performance fluctuates for subjects, and so it's not like you fix a threshold. You're all the time getting close to 75%. So when subjects start drifting up, you make it more difficult when they start. And so what you get is performance which is actually fluctuates around 75%, and you don't not let it, which in the end, on average, when you go at the very end of the experiment, it's not exactly 75%. It goes between 73 and 77, but it's always very close. So you're trying to dynamically adjust performance to this value. You're reading performance and you're adjusting. It's not like you fix a threshold and then you run the experiment with this threshold for 1 hour. You're all the time changing. In this experiment, you could do it the other way around. Everything has, it's a compromise.
Okay, thank you very much again.